Assalamu alaikum. My name is Dilbeg and my partner name is Man Altaf, and our topic of presentation is verifying efficient embedding of a verifiable assembly languages. Our content है introduction, expressing assembly language, verifying assembly language, calling assembly from C, correct and secure DSL interoperations, case studies, evolution, conclusion or references. Introduction में बताया गया कि highly references cryptographic libraries often mix code written in a high level languages with code written in assembly language to spot formally verifying the correctness and security of such hybrid programs as embedding of a subset of x64 assembly language in function that allow efficient verification of both assembly and its interpretations with C code and generates from function f. Verifying high performance software often require verifying code written in more than one language. For example, OpenSSL implementation of cryptographic primarily like AES-GCM and Poly 1305 contain a mixture of C code and optimized assembly language. Expressing assembly language. The embedding use F data type to present x64 registers, constant registers and memory operands, instructions and abstract syntax trees for structured assembly language code. A strict control flow to structure if-else block and while loops which are well suited to our target applications, implementations of cryptographic primitives like those in OpenSSL. A small tested F function not shown prints code value as standard GNU assembly and Microsoft MESM assembly language formats for later assembly linking and execution. Verifying assembly language. Domain specific language DSL embedded in general purpose languages ought to enjoy domain specific benefits not applicable to all host programs. For deeply embedded DSL like well, some common benefits include the ability to easily transform and analyze the syntax of embedded programs. The main idea is to rely on the host language's symbolic computational capabilities to partially evaluate a VC before coding it to the MST solver. Next, calling assembly from C, correct and secure DSL interoperations. In this realm of unverified software, interoperation between language is frequent. For instance, C-like code is convenient for writing efficient low-level code, and it is the standard choice to develop protocols such as TLS. Of course, this will not always be disparable, since we explicitly want to make use of agricultural features exposed only on the assembly language. We do not aim for our DSL interoperations layer to model in-line assembly, focusing instead only on call from C into assembly. Next, a case study. We illustrate well F functionality by porting a previously verified cryptographic algorithm Poly 1305, and we demonstrate value F's scalability of verifying a freshly developed complex cryptographic algorithm AES. These are two of the three algorithms mandatory for the upcoming TLS standards. Next are porting Poly 1305. To demonstrate that value F retain the functionality of well defined, we ported bond ETAL. Verified implementation of Poly 1305, which they provided, ported from OpenSSL 64-bit non-SIMD implementation. This process was tedious but largely straightforward. The lemmas help provide the soundness of the various mathematical tricks that OpenSSL employed to compute operations within a 130-bit field on a 64-bit architecture. Now further will be discussed by the Numan Altaf.
Bismillahirrahmanirrahim. Assalamu alaikum. My name is Numan Iltaf and I'm continuing the remaining slides. A high speed implementation of EES-GCM. EES-GCM from scratch. It is one of the most widely used cryptographic algorithms in the world, thanks to its strong cryptographic properties and real world efficiency. It provides authenticated encryption with additional data, which means that it guarantees both secrecy and integrity for plain text messages, and it can provide integrity protection for additional unencrypted data. Evaluation. This section presents the verification and runtime performance of Whale on AES, GCM, and Poly 1305. All measurements were taken on a single core of an Intel i7 8700 processor, as you see in picture. Verification performance. Developing a whale procedure is typically an iterative process. The programmer writes the code, adds necessary preconditions and desired postconditions, and check for the correctness. To assess the impact of whale by F improvements, we compare its performance to the both whale by F, Nave and whale by Daphne, the most directly related systems. A comparison with each system, for example, developed in COQ, would be difficult without redeveloping many libraries and cryptographic implementations in COQ. A verified efficient embedding of a verifiable assembly language, as you see in a table. Response time to verify each poly 1305 and EES GCM value procedure, and the response time to verify each poly 1305 whale procedure. Verification time whale by F versus whale by F nave and whale by F versus Daphne. All dots below and to the right of the dotted y is equal to x line indicates whale by F outperforming the baselines. Cryptographic case studies, runtime performance. Since the whale by F poly 1305 code is the same assembly code as OpenSSL's scalar code and the SO. OpenSSL implementations. OpenSSL's absolute best code, however, is much more aggressively optimized. It also takes advantage of SIMD parallelism for the GCM computation, as well as several number theoretic tricks that we have not yet implemented. The performance of our verified case studies, including both of our implementations of EES GCM related to OpenSSL, as you see in the table, cryptographic performance. Larger is better as indicates the corresponding implementation does not exist. For EES GCM 128 in Whale by F, we give the performance for the both our low whale hybrid and our primarily whale implementations. Conclusion. We develop a VC generator for an embedded language that is efficient, verified, and supportive of developers. We design techniques to interoperate between a host and embedded language and verified hybrid C or assembly programs. We verified fast assembly crypto implementations. So these are the reference of our presentation slides. Thank you so much.